deep learning for computer vision. We'll not go much into what deep learning is or what is computer vision. We'll see how deep learning impacts the computer vision impact. Okay, so that's a little bit about me. Yeah, you can pull out my LinkedIn profile if you want to get connected. You can connect. You can know more. That's me there with my pet on my farmhouse. Okay. So I really wonder if which one is the jail and which one is the my sunny daytime. So that's the agenda that is what that I have pulled out here. That is food for the thought. Then we go into the historical perspective of deep learning with computer vision and CNNs in computer vision, role of deep learning in computer vision, modern computer vision, and let's see what Microsoft has in store for computer vision and what kind of applications we can do. And we'll quickly go through a demo. I will just go through some code and see how it all goes. So this was some news on internet that IBM has typically stopped working on facial recognition due to human rights. What is it all about? It basically is it privacy, is it technology, or what it is? We'll just get the answer till the end. Till then, you can keep thinking. This is a bit of historical perspective there. In 1959, the first image scanner was invented by transforming images into grids of numbers. Then we go to move on to 1963 with 2D photographs. 1966, in fact, with connecting computer and a camera. Then to the 1980s, we get the very basics of the modern convolutional networks, and so on to 2010. We end up with a Facebook using facial recognition. And the recent history as well here that's been put out here. Right in 2017, the iPhone X having on-device face recognition. Then Alibaba there in 2018, which in fact scored more than Stanford University in reading and comprehension test, basically from images, I guess. Okay. Then we move on to 2018 when Amazon started a commercial sale of face recognition system. Then in 2019, uh, the Indian government announced the face recognition plan for the police officers to search images through mobile app. Then again in 2019, the US added China's leading AI startups to trade blacklist. All this was happening because of advances in AI. In fact, and everybody clashing out which one is better and which one harms the other one for the business. Then there in 2019, in fact, UK High Court ruled that use of automatic face recognition technology to search for the people in crowd was lawful. So again, that brings us to the first question that we had for thought. Why all this part was there? Why IBM stops working on Facebook recognition for human rights concerns? A very ethical question there. So moving further, we move in how deep learning has impacted the computer vision and where the CNNs comes in picture. Moving ahead of deep learning was via artificial neural networks. So initial deep learning networks were all about artificial neural networks, or ANN was what we fondly call them. Then came in the deep neural networks, which could perform complex operations on a variety of media, in fact. And then the ANNs had a couple of drawbacks in spite of having uh, some beautiful uh, technology there. In fact, in terms of their uses in uses as approximators. So what made the ANNs good approximator was they could learn virtually any nonlinear task. Therefore, these were known as universal task approximators. So these again brought the concept of activation functions, which in fact were responsible for incorporating nonlinear network properties. Uh, what does that mean in putting in a simpler terms? It could dynamically they could make us understand the dynamic relationship between the input and output. So number of training parameters dramatically increased. That was a drawback for the ANN. And another drawback was ANNs tended to lose the pixel arrangement of an image. We just move on to see when we see the convolution networks and how this works in where the neural networks in fact work, how this damage was done. This was by very nature, in fact, because all sorts of error, what commonly known as back propagation errors or forward propagation, depending upon the activation functions and the direction they are calculated in. Uh, Moving later, we further we go into the emergence of CNN as a type of deep learning network to process the model. So, what model we are talking? We are talking about the grid pattern. So our images are which are particularly based on grids of pixels. That's why these convolutional networks were very handy. In fact, the very birth of convolutional neural networks was inspired by animal vision. That is the animal uh, eye cortex, which was particularly responsible for the formation of images in animal brains. Uh, we'll see in a bit how this all ended up built with few basic blocks known as convolution, pooling, and layers. So convolution is nothing here but the way in which the networks were connected. Are the neural or these layers were particularly connected, or the bunch of layers were connected. The pooling referred to the way this bunch of layers was connected. Confused? Okay. Convolution is the way these layers are connected with each other. A pooling connects this bunch of layers with each other. So this way, these are fully linked now with each other. So each layer is connected to the another layer, and this particular and one set of layers is connected to the another set of layers. So that's why these are also known as the birth of CNN is also known as the birth of fully connected or fully linked neural networks. Very interesting there. This is a beautiful image of explaining how CNN works, pulled up from Wikipedia. In fact, there's a beautiful entry out there. Down here, we're able to see we have picked up a grid inside the image, which particularly this robot has captured. Inside that grid, there are so many number of pixels, and these pixels are processed layer by layer by layer, and through what? Through convolution. And via convolutions, another set of subsampling happens, and then they again get convoluted to form an output. These are basically as what we are able to read here is it brought infinite capacity for the images to be processed. Like the traditional ML algorithms, which particularly limited us to small data sets and the number of operations we could perform. So this is one type of neural network called convolution. Then another is then depending upon how this particular layers of let's say layers of networks or the set of layers gets connected, or how this particular layer processes the things. Depending upon that, the name differs. Lot of neural networks out there, recurrent neural networks, or more recently the GANs, then more recently the circular neural networks, and so on. So it was in 1998 that the first linear was published. And what is this LeanNet? LeanNet is basically a type of convolution network or a type of algorithms out there in learning, which particularly read the numbers or classified the numbers from the handwritten notes. Uh, Coming to the modern approaches of computer vision, there are two types of algorithms that we can discuss here. That is mass RCNN and YOLO. Both of them are in advanced versions. Max RCNN is in version 3. YOLO is in fact in version 5 as of now. The more recent one is the mass RCNN version 3. So let's because of time constraint and to limit our discussion, we will focus on mass RCNN here on. So Marx RCNN, the original version was presented or published in 2013 as RCNN, which was a four-step algorithm. Uh, First, the input was fed to the network in the form of image. Of course, a very logical step out there. Then the extract region proposals were drawn through algorithms like selective search. Then transfer learning was used for feature extraction to compute features for each proposal. Now, each proposal is exactly basically moving forward an ROI. What is an ROI? Let's see as we move further. For the time being, let's take it as a proposal or a unit there using the pre-trained CNN. Now, this process proposal uh, was used to extract features with support vector machines and further processed to locate out what kind of image it was, or what kind of classification, what classification we want to assign it. Then further in 2015, since this particular algorithm was much more slow, why? We'll understand here is the RF, the region of infrastructure, that is ROI pooling module, was added to the original RNN. So this was particularly absent, and which made this RCNN very slow. And further, ROI pooling works by extracting a fixed size window from each feature map. Well, what is the feature map here? Feature map is, as we can see, the pixels we picked up here. So region of interest is this. This is an image, and this is a particular region of interest where we want to process and observe what is there in this particular image to classify it. So we input an image to associated ground truth bar using a bounded box. So bounded box was found uh, as a new concept here. Now the feature map of extracted ROI was pooled to obtain a vector, and again then the normal process of classification labels and the bar since we had already pooled the ROI and mapped the ROI itself, the bounding map locations of each proposals were also located, and hence the it was classified, or it can be used as an object detector as well. Then coming to the 2018, that is the version 3 of fast RNN, which builds upon the fast RNN version 2, which was presented way back in the 2000, replacing the ROI module with a more accurate ROI line module. So basically, a more advanced version of ROI pooling module was introduced, inserting an additional branch out of ROI aligned. So what does that mean was, additionally it could branch out another region of interest and pool it. So very interesting application of computer vision there by presented way back in build 2017 by Microsoft in their presentation, while showcases the application of industrial computer vision in industrial setups. That is the workplace safety, where is very critical. In fact, these are simple in hardware, simple softwares, which are for solving the very complex problem. So let's go on.
As our world becomes increasingly digitized, so does our ability to connect with it. Imagine if you could search your surroundings the same way you search the web. Using existing cameras and advances in AI, we can now find things and people in the real world in real time and take action to improve safety and well-being. When a dangerous spill occurs in a chemical plant, cameras recognize the incident. Information about the spill is instantly shared with the people who need it the most, enabling them to protect other employees from coming in contact with the hazard and clean it up. This technology can also help keep people safer in hospitals. Patients recovering from heart surgery are limited to how much they should exert themselves. When someone exceeds the prescribed level of activity, a nurse is alerted. What's more, the location of the closest wheelchair is identified, so that the nurse can quickly get the patient seated and safe. This technology is also useful in an environment like a construction site, where people who need specialized tools are spread out, sometimes across multiple floors. Using cameras already in place, this technology can identify a specific tool, as well as the closest authorized person who can deliver it, saving everyone time and keeping the workflow moving. The digital and physical worlds are coming together, to help make everyone more safe, secure, and productive. And we're bringing the edge of Microsoft Cloud to any device.
Okay. So as we saw, this was a typical application which was only possible because the deep learning algorithms were there, in fact. And the deep learning and algorithms now, as we can observe, is not only brought the variety and the speed.
Meet Jim. He works for a giant conglomerate, and every day,
Not only brought the speed and the variety to it, in fact, but they also brought the uh, num different kind of applications to it, which could be mixed together. And if you haven't observed it, they could um, also combine the feature extraction method step into the uh, algorithm itself, and it became a two-way step, in fact, instead of three-way steps. Required in traditional algorithms in terms of getting the image, processing the data, then getting it back, getting it feature extracted, getting it vectorized, and then again going for processing in terms of ML. So this particular three steps were could be combined into two. In fact, the first two could be combined: the data extraction and the uh, feature extraction itself, data processing. Okay, let's quickly uh, go through the demo here, and let's go through the quick uh, code that we have. It's already written there on our internet, but we'll just go quickly, see how it is. Pull out this part of world, the network is a bit slow. There's some commercial there. It just I'm not related to it, but just I have pulled up some website here. And I just thought it was a beautiful article. In fact, it explains the Masha CNN with OpenCV. In fact, so these are the number the pull out. So this is how the code looks like. Then it uses the NumPy library here. Then the uh, traditional random module for time and CV2 module from OpenCV and Python module. In fact, we can pull out the OS module also to handle the files. Uh, uh, Moving ahead, just a quite of little bit construction of arguments there here, and which are required by the mass RCNN. So by image argument, pulling out the image argument, we are trying to read the image. Then we are giving the base part to the RN mass RCNN files. Couple of optional modules there. Not to worry about them for now. Then we move on to the basic IO stuff here. We are just trying to pull out the what kind of objects we want to pull, what kind of marks we want to have, what kind of colors we want to have there on those boundary lines or the bounded boxes there. Simple things out there. So as far as the object class, Coco object class is concerned, it can recognize around 90 classes of objects. So particular people, vehicles, signs, and animals, etc. Then moving on here, we give the weights to each layer. Then we ask the we are loading a image here to OpenCV. And we are giving here we see what is the start point and what is the end point, and for the video. Now this is just drawing the bounded box here, that the region pooling, what we are calling the region of interest, in fact. So mass RCNN OpenCV, uh, we are extracting the region here via the code. So ROI was what I was talking about. We got the clone here, in fact. So then we got a bitwise here. Now this particular function here is very interesting. Instance equal to CV dot bitwise, and so we are vectorizing it. And here we go. Draw the rectangle, that is the bounded box. We put some text if we want to show, and we uh, have a output as well here. Now let's try and mask it. Mask our cars. So going through this, okay, you can always pull it from the lab here. Any particular questions you want me to take till now? So that we can move on and see how the affect how the code is there for the video streams. Yeah, sure. I'll just share the link once we end up. Any question for now? Okay, I'll just share the both the PPT, all three, the PPT in PDF format, and uh, uh, the link to this particular things, and the two papers that we were discussing all about the mass RN, and mass RN was way back published in the 2018 is the full paper is there here. In fact, if you are interested in learning more about YOLO as well, there is the full paper is here. I'll share all those links there in the chat box. Don't worry. Okay, I just put up a lot of messages thanking. In fact, good to know all enjoyed. Uh, yellow, sorry, 7. This one also. Rest there. The other one. Oh, okay. Anything more? Okay, great. We end up here, and I will just post the recording, the link to the recording uh, channels and the website. Hopefully, they if they share it all. Okay, let's this first. Thank you. Thank you all. Bye bye.